Thank you for the invitation, the kind invitation to come to the CMS in Toronto. So I'm going to describe work done in collaboration with a number of people, and in particular, so my main collaborator is lasers dead, so sorry. Yeah. So especially Richard Zinsmeister from Orléans, and a number of students, essentially from Vietnam and China. So it comprises the work done in 3 papers, and I will try to describe the findings without that. There are a number of equations, but I don't need to read them in all details. And it's on so integral mean spectrum of SLE. I don't know if everybody here is familiar with SLE. SLE stands for Schramm-Loewner Evolution. And
it's the big button on the top. Yeah.
And this is, so the version I'm going to take is the whole plane Schramm-Loewner Evolution. It was in gravity theory and actually theoretical physics for what concerns, conformal field theory or critical phenomena in the plane. It was a revolution in '99. So since then it has exploded in gravity theory with 2 field medals, but there's still work to be done on SLE. And in particular, for whole plane SLE, so this is actually, so Ft, so it depends on time. So Ft is a conformal map depending on time. It acts on a point Z inside the disk, the unit disk. So you map the interior of the unit disk to the complement of a slit, a random curve, which is a red curve here. So this is a whole plane SLE, and there is a point which goes, I'm sorry, the laser is dead really. So I think the probably battery is too weak. So see, there is one point going to infinity. The origin is mapped to the origin. And essentially when time flows, so this is a typical Loewner equation on the bottom. So there is a partial differentiation with and STOC is an analytic function. And you obey this equation, and there is a source term, which is very important, which is this lambda of t here, which is, in the case of Schramm, that was the invention of Schramm, the main idea was to take as a source term along the circle. This term, lambda of t is on the circle, the unit circle was the exponential of a ground motion with certain coefficient kappa, which actually tells you what kind of SLE you have. And here in this work, in the latest work, we also added a drift term to the ground motion, which makes things a bit more complicated. And there are, you have a boundary condition at when time goes to infinity. And then if you take the special case of kappa equals 0, which is non-random, since the BT term is 0, and A equals 0, no drift. If you do that, lambda is equal to 1, and in this case you get, as a solution of your equation, you just get what is called the Köber map, which maps the interior of the circle, of the disk, to the complement of half a line. So actually on the real, half a real line here. So that tells you, and when kappa is non-zero, of course, you get a purely fractal curve, which is fractal at all scales, a real continuous fractal curve. Of course, not drawn properly here. And if you, so now if you, in this case, a drift term, which is kind of new item here, if you have kappa equals 0, so you are in the deterministic setting, and you let A non-zero, then you get a logarithmic spiral. So if you mix kappa and A, both being non-zero, you are going to have a logarithmic spiral, which is made of a fractal, looking like SLE. So it's an SLE which is winding infinitely. And there is one important thing here to understand that these are all conformal maps. So you have a lot of latitude in the plane to do a lot of transforms. And one you would like to do, which is 1 over f of 1 over z. So it means you make an inversion to the exterior, and then you also make an inversion of your image. So since your image was a semi-infinite curve, if you do an inversion, you are going to have a finite curve, now with 2 tips. One, the first tip, which is the image of the tip here, and second tip, which is the image of infinity at 0. And this is actually, so of course the first version I have the whole plane, which is from the interior to the exterior to the complement of the curve, is called the unbounded interior version. And here, if you do this inversion here on the bottom of the slide, you have the bounded exterior version. Exterior means because you map the exterior of the disk to the component of the final curve. And this is version actually used in their work by Beliaev and Smirnov, Smirnov in 2010 years ago. So I spent some time on this slide because this is the image you have to keep in your mind. And what we have been interested in is actually what is called the integral mean spectrum. But since you probably don't know it, I'm going to start with the most complex one. So I'm going to make non-real but complex and even and generalized. So with only one slide. So you take a Riemann map, so a conformal map, like the f of t we had before. Typically later my phi will be f at time 0. I forgot to say when time flows on the SLE, what happens is that your curve recedes. So when time goes from 0 to infinity, you actually erase your SLE. This is what happens in that version. Okay, so back to the integral mean spectrum. So you get one of such conformal map. It will be random in our case. And then for PQ reals, you define a general integral means, which is this kind of integral. You put yourself inside the disk and you integrate on a circle, close to the boundary. So little r is going to go to 1 later by lower values. And here I mean generalized because here I have both a moment of phi prime, the derivative, and a moment of phi itself. Usually the integral mean spectrum is defined for q equals 0, so it's really the modulus of the moments of the derivative, because it describes the roughness of the curve. It's also being a multifractal spectrum later. Of course, it will depend non-linearly on p. And here we put a factor moment q of phi itself. You will see later why. And of course, if phi is random, the simplest thing you can do is to take things in expectation. So you will take the integral of the expected modulus. And then you define what is the integral mean spectrum, the spectrum, the multifractal spectrum. In general, you take a lim sup, but if the limit really exists, you are going to take the limit of the ratio of the logs, meaning that if that limit exists, essentially you are going to extract the way this integral moment I or its expectation blows up when r goes to 1. So essentially you have here a spectrum, a double function of p and q, which is a critical exponent, but since it depends on p and q, here two variables, it's a multifractal spectrum. So the aim is to find that beta for the whole plane SLE. And of course, I forgot to say, but you can also, in the setting I've chosen here, you can take p and q also complex, because modulus is outside. And then it describes other, so I forgot to say, it describes by Legendre transform actually the properties of the harmonic measure on your fractal, on your SLE in our case, and also the logarithmic spiral rotations, local ones inside your fractal. Because locally points can be fractal, they just have local dimensions for the harmonic measure, locally along the SLE, and also they can also be made of tiny logarithmic spirals at all points, which are with changing rates. So there is a whole description of harmonic measure and logarithmic rotations along the curve, originally due to Binder as a theory, maybe 20 years ago, and who is also a collaborator of mine actually these days. And so I'm going to actually try to find here the general formula. So let's move on. So why to choose a generalized integral mean spectrum? Why to take both p and q? That's because you want to treat both the bounded and bounded cases simultaneously. So let f be the unbounded interior whole plane, meaning the mapping from the interior of the disk to the complement of a slit of the curve. Right? So that Fp will be F will be the conformal map. So the standard moments will be F prime to the P, taken in modulus. That's standard integral mean spectrum. But suppose now you do the inversion. So you do the inversion, you take this F minus 1, which is 1 over F of 1 over Z. if you calculate the derivative, which is a bounded exterior whole plane, if you calculate the derivative, you of course, at the moment, you of course find, you find this formula here, which is f prime over f to the p, and the f downstairs is to the 2p. The z to the minus 2p doesn't play a role because you are going to approach the boundary. So it means that here you have a factor for f itself, which is 2p. So it means in your plane, your PQ plane, if you take q equals 0, you have the standard spectrum of the whole plane SLE from the interior. But if you take the exterior version, which is bounded, you are going to find your spectrum, the standard spectrum, because it's f minus 1 prime to the p. You're going to find it from the first spectrum for q equal to 2p. So along a certain tangent, a certain line. If you want to find the, say, the logarithmic moment of the moments of log of f prime, it will be f prime over f to the p. So it means if you want to look at the moments of the logarithmic transform of f, it will be q equal p. So there are many reasons to introduce this generalized spectrum. So just a way to unify the whole setting. And so how you do, so the first approach we did was to take, so I take here P and Q real, so I go back to the simplest case, and I take no drift, A equals 0. Remember, A was this drift you had in the SLE source term. And P and Q are just moments. So you define two expressions, one which is a complex, which is the expectation of f prime, so you take half of the moment to the left, and the g of z and z bar is a complete function you need, because so z to the q doesn't play a role, but f prime to the p and f to the q are exactly the moments you want to the right. Okay, so to the right, you recognize the expression you would like to control. So you do it locally at point z. And if you work properly and use SLE and Ito calculus and martingale series, you are going to find then both f to the left and g to the right are obeying differential equations. And the first one for f is simple, that's here. And the second one for g, which is the one which really interests us, is the second one to the bottom. So you see, it's just the addition of both equations for z and z bar. So actually, z and z bar are like independent variables in this kind of problems. It's a bit like in string theory or conformal field theory. And if you look at what happens to g, which combines the holomorphic part and the anti-holomorphic part of your random map, well, what happens, the only difference to the sum of the two, as if z and z bar were the same, were independent, except that now there is a coupling here between z and z bar by the square. So it's not the addition of the two differentials, just a square, and that actually is going to create the singularities of which you are going to detect in the whole plane integral space.
So G depends on z bar because of the modulus.
Yes, because you see on the right, on the top, is just the exponential of the product of the function to the left times the same function to the z bar. Actually, as you will see, the solutions, sometimes you can put them at z1 and z bar 2. You can even split them. That's what happens here. So, so there is actually a little bit of what is called nowadays integral probability, because there are some cases, some values of P and Q for which you can find exactly the solution. So I give you the simplest one. So if you, in the PQ plane, so you are in P and Q are real, so you are in the PQ plane. And if you parameterize P and Q as here, with a gamma here, so that's actually a parabola. Along this parabola, I'm going to show you a few examples later. So it depends on kappa, of course, the kappa of the SLE. Along that parabola, you find actually this exact solution here. So you see f, here there is a gamma. So gamma is this parameter here. We define P and Q. For P and equal P of gamma and Q equal Q of gamma, you find this G here. So as I said, they are really split. So, and it depends on gamma here. Like here, you read the singularity. Because when you put Z1 equals Z2, then you have 1 minus Z bar, which is R squared, to this expression, which is that. So here you have just a very simple solution. Then you see that indeed this correlation function blows up when you approach the boundary. Okay, so that's and this is explicit. So if you want pictures, these are the pictures. So you have these are the integral parabolae for different values of kappa. So in the PQ plane. So this is typically along this curve, you know exactly how to solve your problem. Of course, there are others. So there are other parabola downstairs. There is an infinite series of them. The next one, you can solve it, but it becomes more complicated. You have a combination of two hypergeometric functions, as with an explicit blow-up, which you also find. And then later on, we have not been able to. So you have equations, but you don't exactly know what kind of function now. So this gives you a little hint of the solution, but not the general solution. So what happened is that the end of the study is that actually you put yourself in the PQ plane and you look for this beta spectrum. Remember the blow-up of the model of the moments near the boundary. And this is the answer you get. So the answer you get is that, so it looks a bit complicated, but essentially you have five zones. You have zones, so in between, it means essentially in this is a straight line. The straight line is a branch of parabola, a quartic. So to the left here you have a certain spectrum beta tip, there's a certain beta 0 here, and beta lin here, and then there is a zone here below the green one and the light blue one, where you have a spectrum which depends on both P and Q. And then and above this line, the beta tip, and beta 0 and beta lin, they depend only on P. The reason is that when the part which depends on Q is sensitive only to the fact that F, the mapping can become infinite. So that is going to act only for negative values of Q. For positive values of Q, you are not going to see any divergency generated by the fact that you go to infinity. So remember I showed you that for the bounded case, which is the third case, you should follow the line Q equal to P, and which is this one. Remember the bounded whole plane SLE, the one of Beliaev and Smirnov outside version of my whole plane SLE, the bounded one, which has a tiny curve as an image, and that was Q equal to P, which is this line you have here. So there is a thin line which goes a diagonal line. So if you follow that line, you see that you never enter the beta 1 region. So it means for this version, you are not going, in principle, not going to see any spectrum except for the beta t, beta 0, beta lin, which I have not shown to you yet, but which are the standard ones, which were known since, actually I found them in physics, we found them a long time ago. They were rigorously derived by Beliaev and Smirnov, but corrected by work with Beliaev, myself, and Zinsmeister recently. So these are the two spectra. So just you see this kind of explicit expression, and they depend only on P, and of course on kappa. Now suppose, and so I should mention that there are almost sure versions. This is for expectations. There are almost sure versions by these people, but I'm not going to speak about this here much. So you don't look at all the details, but you have, so actually beta tip is for the P lower, beta 0 is the bulk spectrum, the standard one, and then the linear one. So this actually, they look like this. So to the left you have beta tip, red. The blue one is the bulk spectrum, the standard one, the standard SLE spectrum, which you can define in many ways. And then you have a light blue one, which is linear. So this is what you find, and you find these phase positions. And the phase position corresponds to the vertical lines we had. I'm sorry, I cannot use you have the vertical line, so you follow your diagonal, light diagonal, and you cross D0 prime and D0. This is when you have the phase positions. Okay, so this was known before. And now go back to the phase diagram, and suppose now you find, so what is this beta 1, which I did not show you before? Beta 1, the only one which depends on Q, is this one here to the bottom, which we found some years ago. And now suppose you follow the standard, suppose you follow now the unbounded whole plane SLE line, meaning Q equals 0, which is the original problem for the unbounded SLE, the original version I had. And then you follow the Q equals 0 line on the diagram, and you see that you start at beta tip, then beta 0, and then you cross the green line, and then to the right, you are in the beta 1 region. So it means that if you look for the unbounded version of your SLE, you are going to have the following spectrum. So, remember, it's this one for Q equals 0. So this is the blue equation here for Q equals 0. And so this, on the bottom, this is the drawing I made before of the standard spectrum, beta 0, beta tip to the left, beta 0 in blue, and then the linear part. But because there is a phase transition with this expression here, actually what happens is that the true spectrum is this one. So to the left, the red is correct, the blue is correct, and then you don't go to the right part, you move along the green one. So indeed there is a phase transition, which was not understood before. Let me, how much time do I have?
Still have about 5 minutes, five or six.
No more,
Yeah,
because he started.
yeah, a little more than 5 maybe. Yeah.
Yeah, I started before. Yeah, it's important because it's carefully, anyway. So, what I wanted to say, so go back to the Beliaev spectrum. And so it means we go back to the, so I zoomed, let me just show you, I'm going to, I'm zooming.
It's purely imaginary. This
Pardon? No, there is no imaginary.
Oh, there is no, you have
No,
one.
don't worry, no. So I'm following the Beliaev sphere of lines, the Q2P line. But so in principle, there was nothing happening. Beta T, beta 0, beta lin, just a nice spectrum. But actually, if you look at it carefully, you see that your line, Q2P, actually crosses the continuation of the green line, but it's still above the quartic, so it means you're still in the beta tip spectrum, but except that you cross. And then if you cross a line like that, you should be careful, because something is happening nevertheless in the mathematics. And what happened actually is that there was a gap in the proof of Beliaev-Smirnov, which was due to the fact that suddenly their solution, approximate solution, was becoming negative. Due to this transition, sub-transition, and the upshot, which we repaired with Beliaev and Michel Zinsmeister, is the fact that you have the green spectrum, the blue spectrum beta 0, which is superseded by the beta 1 for Q equal to P, the green one, except that the red one still supersedes. So it's correct that you still have blue and red when you go to the left, except that you have this green lurking behind, which you would see if you were not looking at the tip. You were integrating away from the tip. But of course, the proof actually collapsed, so you had to repair it, and that was useful. And finally, I want to go back to the complex ones with drift. So let's go back to the definitions. You have F, a whole plane. So from the interior of the disk, right? So I go back to the unbounded version, the original one, from the interior to the complement of semi-infinite slit. And you have F, you have G, F before, P and Q, but now they are complex. And also imagine that there is a drifter A. So what do you find? So you find that your PDEs are changed, slightly changed. You see that you have an extra I8 term here. You have an here 2 in the main equation. You get the real part by adding. You get the only difference in this and this real part. And of course, the fact that Q and Q bar. To make the analysis of this, I didn't speak about the way you solve these things, but you have to do to use sub and sub solutions, super and sub solutions. So there is a technique due to Beliaev which we have to extend. So we have two kinds of proof. For the complex ones, we don't know yet, and that's more complex, especially when you have the drift. Nevertheless, what happens is that we still know the spectrum, which is a recent work. So, and the spectrum is given by, so you see I just defined S, which is beta 1 minus the real of P plus 1, called the packing spectrum in fractal analysis. It's given by this formula, you see. You see it's the same formula as we had before, same time, 2t plus 1/2 minus 1/2 square root of 1 plus kt. Like the t itself is a complex combination of P and Q and A. So try to do that, you will see it's not simple. And the way we access it was using Nguyen quantum gravity and KPZ. So it means there are techniques which have been actually originally defined in theoretical physics, which allows you to move from the setting when you have Euclidean measures in the plane to the Liouville random measure. which has been studied a lot by people like Sheffield, Miller, myself, and other people. And when you set yourself with a random measure, things become much more simple. So there are ways to calculate this spectra, and then you have a famous relation for KPZ, or Knizhnik-Polyakov-Zarmodikov relation, which allows one, which we actually with Scott Sheffield proved rigorously 10 years ago, where it allows you to come back from your setting with random measure to the setting of the Euclidean measure, the Lebesgue measure. And if you do that and use tricks, you are going to find that formula. So, and then if you look at the so if now that was, remember, for P, Q, and complex. So here you have the real part of the modulus, P and Q complex and A real. And if you take now P and Q real because you want to go back to the PQ plane, if you do that, you are going to find that explicit expression for beta 1. So you see in terms of T, where T is this reduced variable which has an explicit expression of A, P, and Q. That was the real case before it was a complex case. So that is the spectrum you get. You can reduce the whole analysis I did before. So now you have your kappa and A, because you have the winding, you have the drift. And I think if you remember, this is Q minus P, before it was Q and P. So I just tilted things. And you have the Beliaev line, this is the Q equals 0 line. And you see that you have this kind of spectra now with A, depending on A. So when A is not very big, you still have the same kind of things happening as before. But when A becomes bigger, from right here, you see that suddenly along your orange lines here, or golden lines, you see that one is for the first bisectrix is for the bounded case. The dotted one is for the unbounded SLE. You see that along this line, for instance here, you no longer still the beta lean, beta 0. You enter the beta 1 and then the linear case. So you have a lot of transitions. That's it for cap. And so once you put enough rotation in your drift, and this is the case, kappa equals 6 calculation, A equals 2. So again, as before, you just, for instance, the bold orange line goes from beta tip to beta 0 to beta lead. So nothing, and the dotted lines just enter the beta 1 as before. But if you increase A, put more rotation to your SLE, then you are going to indeed, for instance here, this one does the same as before, just a standard spectrum, but this one enters the corner linear case before becoming beta 1. So that's with this.
Any questions?
Yes. A general question. So, what's the geometry or the physical meaning of this phase transition? So, your spectrum.
That's a good point. Beta tip corresponds to the fact that you see you have a whole plane SLE goes to infinity. In beta tip, you see the neighborhood of the tip. In beta 0, you see what happens along the curve. And when you go to beta 1, you see what happens at infinity. That's exactly what happens. And but when you do this is for the semi-infinite, the infinite version, right? The whole plane, the unbounded whole plane. If you take the bounded whole plane by inversion, you have a small curve with two tips. One is the standard tip with beta tip, then there is a bulk, and then there is a second tip which is the image of infinity, and this one doesn't contribute, it's superseded by the other tip. But if you integrate along the curve and the second tip, not the first, you are going to see the dominance of that tip, which also created the collapse of the proof.
And when you have the drift?
When you have the drift, you have to understand that this is the same thing, except that your curve is drawn on top of a spiral. And this spiral, you have chosen the logarithmic spiral. The A term tells you exactly what kind of spiraling rate you have. So it's a spiral plus an SLE. And that again is telling you that the beta 1, which depends on P and Q, corresponds to the point at infinity again. But if you bring it back to 0 by inversion, it's a point which is also spiraling, and that contributes to the spectrum. That's the second tip, which is spiraling. The first one is also spiraling. So thank you for the question, because that's exactly what is underneath. And if you take a chordal SLE, you're not going to see that. You're going to see one tip, the standard tip, the bulk, and nothing else. Because you start from the boundary. So you don't have the possibility to have the second tip or the point to infinity.